Hello, welcome to everyone in this video. This is our lecture number 10. You all know that is the from lecture number 1 to 7 we discuss the solution of the differential equation. Mainly we discuss about the Frobenius method and then discuss about the legendary polynomial, Bessel function and Hermite polynomial, right? Uh, if you watch this video you know that. If you don't watch, I request all of you first you watch these things such that you can understand this lecture, because it depends on Bessel function, right? And lecture number 8 and 9 mainly consists the partial differential equation with the method, that is the separation of variable method, and we discuss lots of example in lecture number 9. Okay, in this lecture, that is 10, we want to discuss about the solution of Laplace equation in the cylindrical symmetric boundary condition. Okay, let's start. Look at the syllabus. This portion already covered from lecture number 1 to 7, and this portion we discuss in the series, that is the lecture number 8 and 9 discuss this portion, and lecture number 10 in this lecture we want to this cylindrical part. Okay, so you all know that is the Laplace equation will be like that, get square v equals to 0. In the cylindrical coordinate system this get square will be like that. Okay, so if you derivative with respect to this one, you will be get this two term here, and this is the same. Now use this method, that is the separation of variable. Just take is a function of r, phi and z. This is capital Phi, this is small phi, this is capital Z, this is small z. So partial derivative and taking partial derivative, after that if you put in this expression, in this equation if you put, you will be get this one, and just taking out this z value, this is the function only z, this depend only z, that is this separate out, so we can take this separation constant. So after taking separation constant you can see this is having the solution like that. Now if you take this another part in arranging the in like that, so this phi part is also separate out, taking this L square, another separation constant, so phi solution also obtained. So we got the z solution and phi solution, and this remaining part, that is the r equation, will be like that. If you already know, so you can identify this equation. If you substitute this substitution, that kr equals to curly r, and taking this k equal to d curly r by dr with respect to r, so dr by d capital R by d small r will be rearranging like that. So this value is k, so this is k, taking another derivative will be get this. So putting this expression in this equation, you can easily find out this equation, and you all know that this is the Bessel's differential equation, and whose solution will be Bessel's function will be like that. This is first kind, this is second kind, this is the total solution. The linear combination of these two will be the total solution. So this is the total solution of this partial differential equation, that is the Laplace differential equation in the cylindrical coordinate system. Now take an example. This is a cylinder. Within here, this will be the symmetry with respect to phi. That is the phi symmetry. So this is the independent of phi. So there will be no phi part will be arises here, right? So there is independent of phi. So there is no phi part in the solution, because this is independent on phi. Okay, and since this is a finite value within that region, so you must this exponential diverge value will be 0, and this is also diverge, so these two must be 0 in this solution. So the solution will be like that. Okay, now use this concept, that is this will be 0 at this boundary condition. That's mean at the particular value, you know, these zeros of Bessel function is not a periodic interval, it will be discrete, and it will be find out in a tabular form. Will be the table will be also will provided in the previous lecture. You can watch the Bessel function, and the after lecture you can get this table. I think in lecture number 7 we obtain the tabular form for the Bessel function. So the special solution, that is that particular x value, this will be the 0. So since this is the 0, so from here we will be get this solution with a discrete value like that. So the total solution will be the summation. Clear? Now using this another boundary condition, that is at this z equals to 0, that is the base, at this base, this u equals to this equals to 0. So this becomes like that. Using the Fourier coefficient, this constant will be obtained, will be like that. Okay, so using this recurrence relation of the Bessel function and put this z equals to k n r, you will be get this equation, and integrating you will be get this value of the en, and putting this en the coefficient, you will be get this solution. Clear? If this is not a t0 is constant, then there this is phi dependent. This, if this is phi dependent, this also arises, and this can be also the constant can be also obtained from this process. Just multiply this one and then integrating, they will be get this constant cnm, and if you multiply with that one, will be get the constant nm. Clear? So this is the solution for the differential equation in partial Laplace differential equation in the Laplace equation in the cylindrical coordinate system. Look at the an example. Using Laplace equation in cylindrical coordinate system, solve the problem in cylindrical heat flow. Find the expression for the temperature at any distance r from this axis. So you need to find out the temperature at any distance from the axis. Okay, so Laplace equation will be like that, which can be written in like that. So since this is the symmetrically, with respect to phi and z, so only these are independent of this, so this two term is 0, so only r dependent part is arises. If you integrating these things, you can easily find out this solution. So this constant a and b can be find out by using this boundary condition, that at t equal to t1, at r equals to r1, temperature is t1, r equal to r2, temperature is t2. Putting these two equation, you will be get this one, and just take the difference, you will get the constant a, and if you multiply with respect to this one into ln r2, and this is multiply by ln r1, and just rearranging them, just minus, will be get the constant b. So obtain this value a and b, just putting this value and rearranging, you will be get this solution. I think clear. This is all about me. This is my contact details. You can connect with me this Telegram channel, and there are also a Telegram group, and this is my YouTube channel details. Go to this channel, you will get different physics related videos like this session. If you learn something from this session, share this video to your friends, either he or she also get benefit from this video. Subscribe this channel if you need this channel. Those already subscribed, thanks for subscribing. Press the bell icon to get the notification of upcoming video. So in the next time upcoming video, we will want to discuss the spherical polar coordinate system solution for the Laplace equation. Okay, so take care. We'll meet in the next video as soon as possible. Thank you.